A swarm of over 2,000 earthquakes a day, rising magma, and seafloor swelling, axial seamount, a massive underwater volcano 300 miles off California's coast, is waking up. Social media screams tsunami danger and USGS panic. But what's really happening? This isn't a disaster. It's a once-in-a-decade scientific opportunity. Located 1.4 kilometers beneath the Pacific, Axial is quietly preparing to erupt. In this episode, we separate the hype from the data and show why scientists are more excited than afraid. Headline hype versus hidden reality. In May 2012, a viral post claimed the USGS was raising alarms over axial seamount, warning of imminent tsunamis and coastal destruction. Alerts spread across Facebook, X, and Instagram, prompting panic among West Coast residents. But the seamount lies about 1,400 meters underwater, over 300 miles off the Oregon-California coast, far too deep to threaten land. The U.S. Geological Survey monitors seafloor activity there for science, not public danger. The truth is less dramatic, but more fascinating. Axial seamount is a scientific goldmine, offering real-time insight into submarine volcanism. Its inflation and earthquake swarms are tracked via seafloor cables and ocean observatories. These data help scientists understand deep Earth processes, not sound alarms. There's no tsunami threat here, said a USGS volcanologist. Instead, we've tapped into one of the world's best live monitors of underwater eruption cycles. Media dramatization isn't unusual. Headlines feed on fear, yet the underlying science is calm and methodical. Seafloor depth and eruption style make this volcano inaccessible, even invisible to land. But being hidden doesn't make it irrelevant. When we shift the lens from panic to precision, the story becomes one of scientific opportunity, where technology, tectonics, and telemetry converge thousands of meters below the waves. By untangling sensational visuals from actual risk, we show how science works, even in extreme environments. Our story isn't about alarm, it's about awareness. Remote volcanism matters, but not because it threatens us. It matters because it teaches us about Earth systems. Let's dive beneath the hype and into the heart of deep-sea discovery. Now that we've separated fear from fact, it's time to understand the subject itself. In Section 2, we'll explore what axial seamount actually is, a submarine volcano located at a tectonic ridge and hotspot intersection, discovered in the 1980s, and having erupted in 1998, 2011, and 2015. We'll look at its effusive lava, hydrothermal vents, and the unique ecosystems that thrive there. What is axial seamount? Axial seamount is a submarine volcano situated about 480 kilometers to west. There's 300 measurements off the coast of Oregon and California, resting approximately 1,000 meters beneath the ocean surface. It lies atop the Juan de Fuca Ridge, where tectonic plates diverge, and benefits from an underlying hotspot, a rare geological pairing. This combination creates a highly active volcanic site, monitored closely by researchers. First discovered in the 1980s via deep-sea mapping missions, axial seamount erupted in 1998, producing pillow lavas and hydrothermal plumes. Further eruptions occurred in 2011 and 2015, each confirmed through direct measurements of seafloor uplift and seismic swarms. Unlike explosive volcanoes, these events are effusive, emitting lava through cracks and fissures without generating ash plumes or explosive blasts, minimizing surface impact. Eruptions here also support thriving deep-sea ecosystems. The seafloor vents release hydrothermal fluids rich in minerals, creating ecosystems around black smoker chimneys. These vents sustain unique organisms, tube worms, vent crabs, and chemosynthetic microbes that survive without sunlight, relying on chemicals expelled by the volcano. This ecosystem interplay makes axial seamount both a geological and biological point of interest. Today, scientists view the seamount as a natural laboratory for submarine volcanism. It allows studying geological processes in real time, lava flow, vent formation, and ecosystem response, all on a volcanic cycle every 6 to 8 years. Rather than a threat, axial seamount is a model of seafloor dynamics, seen through the lens of modern oceanic science. With a clear picture of what axial seamount is, we can explore why it's back in the news now. Section 3 examines current seafloor inflation, daily earthquake swarms, magma accumulation, and the use of AI to recognize eruption precursors. We'll see how the seamount's activity has escalated since 2024, hinting at a possible eruption and showcasing cutting-edge monitoring techniques. Why the buildup now? Since 2023, seafloor sensors have recorded significant inflation of the axial caldera, mirroring patterns seen before. Its 1998, 2011, and 2015 eruptions. Pressure from rising magma swells the volcano, pushing the summit upward. Alongside this, researchers have tracked more than 1,000 small earthquakes per day, tapping into a seismometer network connected by undersea cables. Geodetic sensors, like pressure transducers, tilt meters, and strain gauges, have confirmed magma accumulation in a shallow reservoir beneath the summit. This behavior signals an active growth phase. In 2024, an AI algorithm designed to detect tremor patterns flagged swarms resembling those of past eruptions. Though scientists caution that timing is uncertain, this pattern adds depth to eruption probability models. After a plateau in inflation during 2023, measurement devices noted a renewed uplift in early 2024, a key precursor. Historically, eruptions at axial follow similar inflation and seismic patterns. USGS volcanologists emphasize caution. The window for an eruption is likely before end 2025, but this is based on models, not guarantees. These signals are suggestive, not certain, said one expert. This combination of deformation, quakes, and data analytics highlights a mature monitoring system, turning a previously remote volcano into a test case for predictive science. We're not watching for hazards. We're watching a cycle, studying it, and honing our ability to forecast eruptions with emerging technology. Sensors on the seafloor axial seamount is closely monitored by the Ocean Observatory's initiative, OOI, using seafloor cabled sensors that connect the volcano's summit to Pacific Northwest shores. The NEMO cable, laid in 2014, runs over 300 miles, about 480 kilometers, from the seafloor summit to shore, carrying real-time data from seismic sensors, pressure gauges, and hydrothermal monitors directly to USGS, Oregon State University, and partner labs. Seismic sensors detect quake swarms, often more than 1,000 events per day, signaling magma movement beneath the caldera. Geodetic tools like tilt meters, strain meters, and pressure transducers measure changes in seafloor topography down to centimeter precision. Hydrothermal instruments evaluate vent temperature, flow rate, and chemical composition, essential for understanding how heat and minerals enter the ocean environment. Adding to the analytical power, remotely operated vehicle JASON, operated by the University of Washington, periodically surveys the summit. During its most recent dive in 2023, JASON captured high-resolution imagery showing pillow lava formations and measured vent fluid temperatures above 350 Kelvin, while also collecting biological and mineral samples. This coordinated system helps integrate seismic, geodetic, and visual data in real time. This underwater network not only supports eruption forecasting, but also serves as a bold example of deep-sea science platforms. As one OOI engineer noted, we can now watch a volcano evolve live from the deep sea. The seafloor array is both our early warning system and our window into seafloor Earth processes. We've seen how sensors keep watch, but what actually happens during an underwater eruption? In Section 5, we'll describe how axial seamount erupts, how seismic tremor begins, lava flows form pillow basalts, the eruption's duration of days to weeks, and how these events reshape the seafloor and sometimes damage equipment. How an underwater eruption works. When axial seamount erupts, the eruption begins quietly, with seismic tremor often lasting about 1 hour. Magma ascends through fissures in the caldera floor at 99 degrees Celsius per meter, generating rhythmic earthquake swarms. These swarms are the seafloor equivalent of rumbling but unseen at the surface, marking the magma's movement from the reservoir to eruption sites. As magma reaches the summit, it flows into fissures that radiate across the caldera floor up to 40 kilometers, by 25 indépendamment. The lava, upon contact with 4 degrees C seawater, cools rapidly to form rounded pillow basalts in volcanic crusts. These formations build new terrain incrementally, creating distinctive mounds and ridges that preserve the eruption's signature shape for decades. Eruptions can continue for days to weeks, depending on magma supply. Post-eruption, swarms of aftershock quakes persist as the crust cools and subsides. Hydrothermal systems react as well. Vent chemistry changes, vent temperatures fluctuate, and nearby sensors may be scoured or buried by lava. In past events, the seafloor changed by 10 to 15 meters in height. Though powerful, these effusive eruptions pose no danger to human ships or coastal communities. No explosive column forms. Instead, hot lava hisses under the sea. It's a subterranean reshaping, invisible from above, but transformative beneath the waves. An eruptive dance that slowly molds the ocean floor. Eruption or no eruption, Axial is also a living laboratory, its vents nurturing unique ecosystems. In Section 6, we'll explore how deep-sea life thrives among hydrothermal vents, tube worms, vent crabs, snowblower plumes during eruptions, and how biodiversity rebounds post-eruption. Ecology of deep-sea vents. Axial seamount hosts hydrothermal vent ecosystems teeming with life in extreme conditions. Chimney-like structures, called black smokers, vent mineral-rich water heated to over 350 degrees, creating a base for chemosynthetic microbes. These microbes support larger organisms like tube worms, vent crabs, and even small octopuses in a world without sunlight. During eruptions, snowblower events occur. Turbulent mixing between hydrothermal fluids and seawater creates white plumes filled with microbial floc and minerals. After the 2011 eruption, seafloor imagery showed planktonic blooms packing the water column, and within 90 days, tube worms and microbes began recolonizing the fresh volcanic landscape. This rapid recovery shows resilience. In less than a year, microbial mats reappeared, and small crustaceans followed. Studies of gene sequences from 2022, vent species revealed adaptations to fluctuating temperatures and chemical mixes. These ecosystems operate on cycles linked to eruption patterns, offering a window into resilience under extreme planetary conditions. As UW marine biologist Dr. Lisa Levin reflected, these vents are Earth's laboratory for life under stress. They teach us not only about biology near seafloor volcanoes, but hint at how life might adapt on icy moon-ocean worlds like Europa or Enceladus, places with no sunlight but plenty of geothermal power. Risk to land and vessels. Although axial seamount is active, it poses no threat to the coast of Oregon or California. Situated about 300 miles, 480 kilometers offshore at a depth of 1,400 meters, any eruption remains deep underwater. Unlike explosive volcanoes, its effusive lava flows lack the energy to displace enough water to generate tsunamis. Even the largest eruptive volumes, tens of millions of cubic meters, fail to reach the surface, keeping ocean swells calm. Maritime traffic in the region is largely unaffected by activity on axial. Ships traversing the Pacific won't see bubbling lava or ash. Heat from the lava dissipates in the ocean's abyss, and the volcano's summit remains 10 kilometers deep below sea level. A seafloor eruption won't set off tsunami alarms. Axial is a submarine spectacle, not a ship safety concern, said a USGS geologist monitoring the site. Similarly, seafloor tectonic zones and axial's effusive eruptions do not interact with subduction zone fault systems or coastal seismic hazards. They are contained to the Juan de Fuca Ridge, far from continental geologic activity. This isolation means that scientists can observe volcanic behavior without worrying about linked quakes or crustal shifts along the continental shelf. Ultimately, axial serves as a natural laboratory, not a hazard to people. The best-case scenario is detailed seismic data in live-streamed vent images. The worst case is sensor damage on the seafloor. It's a safe zone for studying planetary volcanism, and vessels in the Pacific remain blissfully unaware of these deep-sea eruptions. With risk confirmed to be minimal, let's examine how scientists anticipate what comes next. Section 8 delves into predicting axial's potential eruption, detecting seafloor uplift, tracking quake swarms, leveraging AI analytics, and analyzing historical cycles. All this sharpens eruption forecasts before end 2000, perhaps, without panic, but with precision. Predicting the eruption. Since 2023, axial seamount has exhibited clear signs of pre-eruption behavior. Seafloor uplift has been gradual, with centimeter-level deformation recorded by pressure sensors and tilt meters. In early 2024, measurements exceeded the inflation levels seen before the 2015 eruption, prompting closer attention from USGS volcanologists and OOI researchers. Earthquake swarms remain persistent, up to 2,000 quakes per day, often clustered near the summit. These signals are analyzed not in isolation, but through AI-powered pattern recognition, which compares recent activity against eruption models from 1998, 2011, and 2015. Systems like deep learning tremor detectors flag anomalies hours to days before surges in inflation or frame arrival. Based on historical patterns, some experts estimate a probable eruption before year-end 2025, but emphasize significant uncertainties. Magma chamber pressure, eruption volume, and vent timing vary between cycles. The model gives us a window, not a countdown, explained a lead volcanologist. That window gives decision makers and researchers a chance to prepare. This predictive framework offers a blueprint for volcanic monitoring worldwide. By integrating real-time seafloor data, deep learning analytics, and historic eruption timelines, scientists have created a near-live alert system. Whether eruption happens in late 2020 or 2025, it's a demonstration of how science can calmly anticipate, not sensationalize, nature's next act. With prediction tools in place, scientists turn their gaze to the environmental impact, especially the deep-sea ecological response. Section 9 investigates how eruptions shape vent life, snowblower plumes, species die-off, recovery timelines, and what the rebound after a volcanic event teaches us about resilience in extreme conditions. Why scientists aren't panicking. Even as seismic activity and magma indicators climb, experts aren't sounding alarms. First, the volcano's depth, over 1,400 meters, ensures any lava flows remain hidden beneath kilometers of seawater. That alone dramatically reduces surface hazard. No tsunamis, no lava sheets, no aerial ash plumes. In short, an eruption would be an ocean bottom event, not a coastal emergency. Second, axial produces effusive eruptions, which are slow-moving and predictable compared to explosive counterparts. Without steam-driven blasts, impacts remain local to the seafloor. There's no volcanic ash to affect shipping routes, air quality, or beaches. No red skies or evacuations. Even earthquake activity stays confined to the summit region, leaving continental fault zones untouched. Importantly, the volcano serves as a safe test bed for eruption science. Sensors can become buried or heated, but they rarely fail catastrophically. Data networks continue streaming during past eruptions. Continuous monitoring with real-time dashboards means scientists can observe, analyze, and respond from a distance. The event becomes a scientific opportunity, not a threat. Finally, USGS and NOAA clearly communicate that axial isn't a public safety hazard. Responsibility is split. NOAA Ocean Observatories. Initiative manages the mound, while USGS focuses on land threats like Mount St. Helens, Mount Rainier, or Yellowstone. We're not fearing the volcano, we're studying it, said an ocean volcano specialist. It's curiosity, not chaos. Implications for volcano science. Axial seamount's live monitoring marks a pivotal moment in volcano science, offering unprecedented insight into submarine eruption cycles. Until now, scientists relied on satellite observations, geologic mapping, and rare dredge samples. But the 2015 eruption was the first to be observed directly from the seafloor in real time, transforming predictions into data-driven science. It shows how tectonic processes unfold along the mid-ocean ridge, a global volcanic network shaping Earth's crust. This seamount allows research into hydrothermal vent dynamics, where heat from magma interacts with seawater to release minerals and heat. These vents influence local ocean chemistry and provide heat transfer models that represent global ocean tectonic feedback loops. The 2024-25 monitoring cycle, marked by substantial uplift, helps refine models of magma supply, pressure thresholds, and eruption intervals across mid-ocean ridges. Studying axial helps validate numerical models combining volcanic, seismic, and geochemical data. Using machine learning and real-time sensor feeds, researchers can simulate how pillow basalt flows form, how magma chambers refill, and how seafloor ecosystems respond. It establishes a scientific template applicable to other submarine volcanoes, including those near Iceland, the Mariana Trench, and future deep-sea exploration sites. This is more than a single volcano, it's a laboratory for global eruptions, said USGS and OOI scientists. The lessons from Axial extend to planetary science too, understanding how ocean-covered worlds like Europa might host geothermal activity. Scientists now view submarine eruptions as dynamic components of Earth's life system, complex, connected, and profoundly impactful. As eruption science evolves, so does the way data is handled. Section 11 examines how AI, real-time data streams, and public engagement are changing volcanic monitoring worldwide, harnessing modern tools to assess remote, submerged systems in near real time. The role of AI and real-time data. Early prediction at Axial uses AI algorithms trained on patterns from 1998, 2011, and 2015 eruptions to detect atypical quake swarms and caldera inflation. These neural networks analyze thousands of daily seismic events, pressure readings, and uplift signals, flagging eruption precursors potentially hours before magma reaches the summit. This method enhances situational awareness on an active volcano, otherwise hidden beneath 1.4 kilometers of seawater. Real-time data streams from the NEMO cable deliver seismic, geodetic, and hydrothermal information directly to shore. Public dashboards display live seismograms, seafloor displacement maps, and water chemistry results, all accessible to scientists and enthusiasts. This transparency fosters community understanding and encourages broader scientific scrutiny, linking field researchers with classrooms and citizen scientists. Webinars and blog posts hosted by USGS, OOI, and universities explain data trends in simple language. For example, when inflation exceeded 2015's level in 2024, experts provided context on what that meant. Not imminent doom, but possible eruption window. Enhanced communication helps reduce sensationalism and anchor narratives and data. This model, real-time sensors connected via ocean cables, AI-based signal analysis, and open communication, is now being exported globally. Projects are underway to emulate Axial's system at sites like Mariana, Iceland's Reykjanes Ridge, and Hawaii's Loihi Seamount. Axial demonstrates how modern volcano science can operate in high-risk zones, predictively, transparently, and collaboratively. With tools and communications in place, the final sections focus on what to watch and when. Section 12 will outline key eruption indicators and how scientists plan to follow events from seafloor to live webcam, offering a front-row seat to undersea volcanism. What to watch for. As the potential eruption window approaches, the watch list includes seismic rates surpassing 2,000 quakes per day, sudden upticks in centimeter-level uplift, and shifts in hydrothermal vent chemistry, such as rising temperatures over 350 degrees or increased vent flow. These are measurable predictive signals rather than speculative omens. ROV Jason's next deployment is scheduled for late 2025, timed to visually document pillow lava flow and vent morphology changes. Footage downloaded via NEMO will be shared in near real time, offering scientists and the public a unique underwater eruption webcam. This doesn't just support research, it invites public participation in a moment of discovery. Hydrophone networks will also listen for gas bursts, rock cracking, and seismic tremor, acoustic signs, oysters of magma interacting with water. These acoustic data, when combined with seafloor deformation and quakes, form a layered eruption signature, decodable via pattern recognition and AI. Beyond eruption, Long-term monitoring will continue as the seafloor cools and ecosystems regenerate. Observing recovery, biodiversity return, and mineral deposition allows comparisons to past data, forming a life cycle model for submarine volcanoes. A story told in seismic tremor, lava flow, thermal shift, and biological renewal. We've tracked risk, science, prediction, and signals. Now in Section 13, we bring it all together, summarizing why axial seamount matters, not as a threat, but as an invitation to explore, understand, and marvel at Earth's hidden volcanic rhythm. Takeaway and calm, call to curiosity. Yes, axial seamount is restless, with signs of magma buildup, seafloor inflation, quake swarms, and AI alerts. But no, it doesn't threaten cities, coastlines, or shipping. It's deep ocean, not shallow hazard. Instead, it offers a rare gift, a real-time window into submarine volcanic life cycles. The eruption, if it occurs, will be slow, silent, and mostly much unseen from the surface. But its effects, hydrothermal chemistry changes, new lava flows, microbial colonization, will teach us about oceanic volcanism and early Earth conditions. It's pure science, not panic. The technology powering it, cabled sensors, AI analysis, ROV imaging, public dashboards, shows how we can responsibly monitor remote processes anywhere on Earth. This model may soon help assess volcanoes on tectonic faults, oceanic ridges, and even other planets. So follow this story not for fear, but for fascination. We stand witness to a deep-sea rhythm guided by invisible data points and quiet eruptions. That's not alarm, that's awe. No, the USGS isn't panicking, and neither should we. Axial seamount is erupting in the safest place possible, deep beneath the Pacific, far from land. What it offers isn't fear, it's insight. From real-time AI monitoring to deep-sea biology, this underwater volcano is a scientific marvel. The next eruption might not make headlines, but it will rewrite textbooks. Stay curious, stay calm, and keep watching, because Earth's greatest stories often unfold far below the surface.